Hello again, Chem 2 students. This is Mr. Keister here with you. This is the video for Monday, November 2nd, 2020, our scheduled 51st day of school for the fall semester. Always keep in mind, though, that the dates could change for a variety of reasons, but the lessons and the order that those lessons are presented will remain the same regardless. So let's take a look at our do-nows and see what our schedule is for today. We don't have any new papers to pick up today. We started an assignment from last Friday over polarity, intermolecular, and intermolecular forces. I think you were to do numbers 1 through 6 on that. If you want to check your work on that, it is posted on the back board here in class. It is also posted on Canvas on the answer keys page. We will be finishing that assignment after today's lesson, and you will be turning that in, I believe, tomorrow. Don't quote me on that, but I'm pretty sure I'm collecting it. Anyway, so we're going to finish that up today. You had your first polyatomic ions quiz this past Friday. Hopefully that went well for you. If not, remember, I'm throwing out the lowest grade and averaging the other two. So if you weren't ready Friday, I hope you're ready for the next two. All right. Now, we're not taking a quiz today. Today, we're taking a day off from that. But quiz number 2 will be tomorrow. The last few minutes of class. Quiz number 3 will be on Wednesday. And note about that, if you got a perfect score this last Friday and you get a perfect score again tomorrow, in other words, the first 2, then you are exempt from taking quiz number 3 on Wednesday, and you will receive an extra 10 points on your quiz grade, bonus points in the grade book. All right. So today we're going to continue on in our 4-1 notes packet, finish up intermolecular and intermolecular forces that we started last Friday, as well as look specifically at water and hydrogen bonding. We're going to look at metallic bonding, and then some exceptions to the octet rule. Your homework will be to finish the assignment that we started last Friday. And yes, I guess I am collecting it for a grade tomorrow. I thought I was. Make sure you have shown all work where asked to. Okay? All right. So I think let's get ready and get rolling here. Okay. So we finished up Friday talking about the general properties of molecular compounds. Remember, with we have a difference in polarity within covalent bonding, and so the properties of molecular compounds then can vary somewhat. Remember, we can have nonpolar covalent bonding, which is the weakest form of covalent bonding. We then have semipolar, where you first get the establishment of a dipole or partially positive and negative poles. And then polar covalent bonding, the strongest type of covalent bonding, where you have an even more prominent establishment of those partially positive and partially negative poles, or a dipole. And so as a result of that, that range we have from weakest to strongest type of covalent bonding, that the properties then can vary according to that. And we went over that on Friday. Also remember that with the different types of covalent bonding, we have different types of intermolecular forces. With nonpolar covalent bonding, we have London dispersion forces, which are the weakest type of intermolecular force. Remember, an intermolecular force is a force between like molecules, while an intramolecular force is a bond, which is a force found within an individual molecule. With semipolar and polar covalent bonding, we have 2 types of intermolecular forces. The weaker of the 2 is a dipole-dipole force, and the stronger of the 2 is a hydrogen bond. All right, a hydrogen bond, again, is an intermolecular force. It's found between like molecules. Hydrogen bonding only occurs when the compound contains hydrogen and either fluorine, oxygen, or nitrogen, which then lends itself to only 3 compounds. All right. HF, hydrogen fluoride, water, of course, and NH3 ammonia. All right, so only those 3 compounds have hydrogen bonding between their molecules. Ionic bonding, of course, is by far the strongest type of bond, and the intermolecular force there is an ionic force, which is also the strongest type of intermolecular force. So that's a brief review of how we ended up yesterday. So let's talk a little bit specifically about water and hydrogen bonds there. So because of the polarity of the water molecule, it is bonded by polar covalent bonding. There's a strong force between different water molecules that are in close contact with one another. So we have the creation of a dipole by equal but opposite charges that are separated by a short distance. The intermolecular force in which a hydrogen atom that is bonded to a highly electronegative atom, hence fluorine, oxygen, and nitrogen, is attracted to an unshared pair of electrons of an electronegative atom in a nearby molecule is the intermolecular force we call hydrogen bonding. So let's take a quick look at how hydrogen bonding occurs in a water molecule. So if we draw water here, we draw a water molecule, so it looks like this. All right, and let me then draw a second one. All right, so let's go right here. We'll draw another one over here. You get the idea, or these can all surround each other. So anyway, so oxygen's unshared pair of electrons has two pairs, all right? So remember, this oxygen has a partial negative charge around those electrons. Each hydrogen has a partially positive charge around it. And so what happens then is, let's take a look here. Let me draw these partial charges in here. What happens then is this unshared pair of electrons is on one oxygen atom is attracted to the partially positive hydrogen atom from a nearby molecule. And so right here then is where the hydrogen bond occurs. All right, right there, and right there. So it's between one water molecule and another water molecule, between the oxygen in one water molecule and the hydrogen in another. And so you see these just link up, and it just gets bigger and bigger and bigger. All right. And so these right here is hydrogen bonding. Once again, it's not found within an individual water molecule, but it's found between water molecules that are in close contact with one another. Okay. That's basically what a hydrogen bond is. Again, I don't really like the term hydrogen bonding because when you hear the word bond, you just naturally think of, oh, okay, it's a bond found inside a molecule, and when it's actually not. Okay, just want to make sure you are completely understanding of that. So on the next page, hydrogen bonding explains many of water's unusual properties. Its high boiling point, its high melting point, its high surface tension, its large density, capillary action as compared to other molecular compounds that have polar covalent bonding within their molecules, but do not have hydrogen bonding between their molecules. This is what makes water such a unique liquid, all right, such a one that's so essential for life. If it didn't have the properties that it has, then it would not have the value that it has to life on this planet, because all of these properties make water a very, very unique liquid, all right? So, hydrogen bonding and water, okay? All right, so let's look at metallic bonding. So, metallic bonding, bonding is different in metals than it is in ionic or molecular compounds. Metals do not bond with each other because they all want to lose electrons, all right? Their Coulombic force is weak, all right? They don't want to gain electrons. They don't want to share electrons. They want to lose electrons. Because of this, metals do not bond with each other. All right? Sodium does not bond with calcium. Magnesium does not bond with strontium. All right? Iron does not bond with cobalt. Doesn't happen. What we're talking about here, metallic bonding, is where sodium atoms bond to other sodium atoms, or calcium atoms bond to other calcium atoms. All right? So, however, the atoms of an individual metal will bond with each other based on these factors. Again, metals, most of them, a great majority of them, only have one or two valence electrons. All right. In the S block elements, the S1s, the alkaline metals have one, the alkaline earth metals have two, and all your transition metals, D block, and all your intertransition metals, F block, have two valence electrons. So a great majority of the metals just have one or two. Now in your transition metals, you also can have vacant or somewhat vacant d orbitals. And in the intertransitions, you can have f orbitals, okay? Within a metal, the vacant orbitals in the atom's outermost energy levels overlap, allowing the valence electrons to roam freely throughout the entire metal, all right? So what that means is we say that the electrons are said to be delocalized. In other words, they're not just stuck to one orbital, but they can kind of travel in and around that empty space there. So the electrons do not belong to a particular atom in the metal, but can move freely about the metal's network of empty orbitals. These mobile electrons form what is called a sea of electrons around the metal atoms, which are then packed together in a crystal lattice, a rigid ordered structure. So the chemical bonding then that results from the attraction between metal atoms and their surrounding sea of electrons is called metallic bonding. So again, this is found within between atoms of the same metal. All right. Because of this freedom of motion of electrons in a network of metal atoms, several unique properties regarding metals exist. Number one, they are highly electrically conductive, right? They conduct electricity very well, and they conduct heat very well. Because of this freedom of motion of electrons, you can pass an electric current through them as it will travel from electron to electron to electron very quickly. And the same goes with the transfer of heat. Metals have the ability to absorb a wide range of light frequencies, all right? They can go from the ground state to the excited state and back to the ground state very, very quickly. Thus, metals are shining. This is why when the sun shines on a metal, it seems to, it exhibits multiple colors, all right? That's because of this right here. Metals are malleable. They have the ability to be hammered or beaten into thin sheets, all right? You can't do that with a non-metal. Now, you know, aluminum, we use aluminum to build airplanes, all right, the bodies of airplanes. And that airplane body is a very, very thin sheet of aluminum. It's not very thick at all, and yet it's very, very strong. That's because the metals, in particular aluminum, are malleable. Now, you can't pound a non-metal that's in the solid phase, such as carbon, into thin sheets. All it will do is crumble, all right? But in a metal, since you have this empty network of orbitals, there's space in there between those layers of metal atoms that you can push them closer together. And that's what malleability is. Metals are ductile. Ductility, the ability of a metal to be drawn or pulled into a thin wire. Again, this is why we use copper or aluminum or some alloy of several metals as wiring, all right? Because again, they can be pushed together in a much smaller space. They can be drawn into a wire, whereby a non-metal conductor could not do that, all right? So both of those properties are possible because metallic bonding is the same in all directions throughout the solid, meaning that one plane of atoms can slide past another without breaking. This is unique to metals, all right? Unique to metals, in particular transition metals, where you have empty d orbitals. This is why copper and nickel, and again, alloys of those types of several of those types of transition metals are used primarily to make wiring or to make strong type metal surfaces for things such as airplanes. Okay. Okay, so that's metallic bonding. Now let's look at some exceptions to the octet rule. So sometimes it's impossible to write a Lewis dot structure that fulfills the octet rule. In other words, every atom within that compound, within that molecule, achieves its octet. Sometimes it's just not possible. So let's look at some situations where that is the case. Okay. Number one, there's an odd number of total valence electrons for a particular molecular compound. All right, so let's look at NO2. So if we look at NO2, N's electronegativity is 3.04, oxygen 344, and if we subtract those two, we get 0.40, which means that the bonding in this molecule is nonpolar, covalent, all right, nonpolar. So we have three atoms in this molecule, an N and two O's. Which one's going to be in the center? Okay, we've talked about that. Well, nitrogen has 5 valence electrons. It's in group 5A, meaning it has 3 openings around it. Let's go ahead and draw that. 1, 2, 3, 4, 5. 1 pair and 3 singles. And each oxygen atom has 6 valence electrons. Oxygen's in 6A. All right, so which means it has 2 pairs and 2 singles, which means oxygen only has 2 openings. Well, that tells us that the N's going to be in the center. All right, so we'll put an oxygen on either side of it, like so. All right, now, so if each oxygen has 6 valence electrons and the nitrogen has 5, that gives us a total of 17 valence electrons total, which is an odd number, all right? As you're going to see, we're not going to be able to fulfill the octet rule here, so let's look at that. So, well, I can see a double bond forming here between 2 of nitrogen's openings and oxygen's 2 openings, which then leaves us a single bond over here between nitrogen's other single electron and one of these single electrons around the oxygen. So what you end up having is this. A double bond to one O and a single bond to the other. And if you look at that, now look, we could have also drawn this another way. All right. We could have also drawn this another way. We could have put the double bond over here and the single bond over here. Could have just as easily done it that way, whereby it would just be a mirror image of the other one. And when that occurs, that is what we call resonance. Resonance, all right? I think there's a question or two about this on your next mastering assignment, about what resonance is. So when you have the ability to place a double bond or a triple bond in several different places within a molecule, so whereby the molecule then is basically the different drawings you can make are just mirror images of each other, we call that resonance, where there's more than one possible way to draw it. All right, so you might want to remember that term. Well, anyway, however way we end up drawing it, what you can see here is that the nitrogen achieves its octet. One of the oxygens, the one with the double bond, achieves its octet, but the other oxygen only has 7 valence electrons. It does not achieve its octet. There's just no way it can. A coordinate covalent bond doesn't do us any good here because that's where you have a shortage of 2 electrons by one atom. And then you have the other atom that has an extra unshared pair share that with the other atom. That's not the case here. We just have one atom that's 1 electron shy of an octet. So that's not going to do us any good. So the point to this is an unstable compound because all compounds want to have every atom within them achieve their octet. So what happens here? This one of these oxygens, however way we draw it, wants to pick up another electron. And so it's very electronegative, all right? So it gets around something that wants to give up an electron, it's going to bond with it. So let's just say, how about a 1A metal like sodium? 1 valence electron, all right? It would gladly give up that valence electron, and this oxygen here, that short one, would gladly take it. So let's see what happens when you do that. So that means the sodium atom has lost its electron. It forms a sodium ion, Na+1 or Na+. And now that NO2, I'll do the bottom one here. So I got my double bond over here. And now this O that had the single bond to it now has achieved its octet because it picked up an electron from sodium. Well, now that NO2 is not a neutral molecule anymore. It now has a -1 charge, all right? And if you take a closer look at that, you might recognize it as one of the polyatomic ions that you are being required to memorize, which is NO2 -1, which is nitrite. The nitrite ion, which is very stable. All right. Well, herein lies how the polyatomic ions are formed. All right. Polyatomic ions are formed from neutral molecular compounds whereby one or several of the atoms within that molecular compound are short of an octet. All right. All your polyatomic ions, like nitrite, that have a charge of -1, one of the atoms in there is short an octet by 1 electron. And when it gains that electron, it becomes stable and it has a -1 charge. So that's what's happened with all your -1 polyatomic ions. For the ones that have a -2 charge, as a neutral molecule, they are 2 electrons short. So an electron short on 2 different atoms, all right, of achieving an octet. So when they gain those 2 electrons from a metal or whatever, then they become charged with a -2 charge, and they become stable because now every atom has achieved their octet. In a -3 polyatomic ion, again, 3 atoms are shy an electron of achieving an octet, and when they gain those 3 electrons totally, then they have a -3 charge, and again, they become stable. So polyatomic ions are formed from neutral molecules, just like NO2, whereby they are unstable as neutral molecules because not all atoms within that molecule have achieved their octet. That's how polyatomic ions are formed, okay? All right, so next, phosphorus and sulfur will sometimes expand their octet to include 10 or 12 electrons, respectively. All right, so let's look at that. So why phosphorus and sulfur in the first place? Well, let's take a look and see where they're located. Well, phosphorus, I'm looking over the periodic table on the wall. So phosphorus and sulfur are in the P block in period 3, all right, period 3. So they are, let's see, phosphorus is 1s2, 2s2, 2p6, 3s2, 3p3, and sulfur 3p4. All right, so I want you to think about that. They're in a very unique position there, all right? In period 3, which is energy level 3, all right, their s orbital is full, their p orbital is not full, it's getting close. But remember, in energy level 3, there's a d orbital, and it is empty, all right? 3d is not, it doesn't have any electrons in it at all. So this is the key here. There's an empty 3d orbital where additional electrons can be squeezed in there if circumstances are just right. And circumstances are just right when the other element that's reacting with phosphorus or sulfur is very electronegative, all right, very electronegative, such as chlorine or fluorine. All right, so let's take a look at how this happens. All right, you don't see this in any other period. You don't see an expanded octet in period 4, 5, 6, 7. Doesn't happen. You don't see it in period 2 or 1 either because there's no d orbitals in there. All right. As you go down to period 4, 5, 6, and 7, you're getting too far away from the nucleus. Coulombic force isn't strong enough. It's not going to draw in those extra electrons to expand an octet. In period 3, like I said, the conditions are just right for that to possibly happen. So let's look at PCl5. So P is 2.19, Cl is 3.16. The difference in electronegativities there is 0.97, which gives us a semipolar covalent bonding. All right. So P, of course, has 5 valence electrons, 3 openings. Chlorine only has 1 opening, 7 valence electrons. So P is going to go in the middle. So let's just draw phosphorus. Let's see, 1, 2, 3, 4, 5. And then what you can see is there are 3 openings there around P. So let's go ahead and put a chlorine around each of those 3 openings, for starters anyway. You say, no, wait a minute. We're looking at PCl5. This is just PCl3. You're right. PCl3 is the normal molecule that exists between phosphorus and chlorine, all right, whereby all of these have achieved their octet. But we're talking about PCl5. Well, where's the only other place that these two extra chlorine atoms could hook on? Well, and that is this pair of electrons, this unshared pair around P. And that's exactly what happens. So we're going to put a chlorine on each one of those. And like I said before, the only reason this happens is that there is extra room in there for those for those 2 atoms to squeeze in and share those electrons because phosphorus has an empty 3d orbital. All right. So here's what you get. You get a pretty big molecule. Get all these dots around the chlorines. I want to forget those. So I want you to take a look at that. So each chlorine has achieved its octet, but I want you to look at phosphorus. It's got 2, 4, 6, 8, 10 electrons around it. This is unstable. Right? There's 10 electrons around the phosphorus. Does it like doing that? No, not really. It would much rather be PCl3 like we talked about a little bit ago. And so what normally happens is that this thing breaks down and you get the normal molecule between phosphorus and chlorine, which is PCl3. And then those other 2 chlorine atoms break off of there and bond with each other. And we get a molecule of Cl2. All right. So this is the stable situation here, normal octets for everyone. But I want you to see that this compound, PCl5, does exist. All right, it does exist, whereby phosphorus has expanded its octet from 8 electrons to 10. Again, this is unique to period 3, unique to phosphorus and sulfur. All right, it's not a stable compound. It would much rather have a normal octet, and so that's what it usually does. But under certain conditions, this compound certainly can form. Sulfur does a very similar thing. All right. So let's look at SF6. So sulfur is 258. Fluorine is 398. And if we subtract those 2, we get 1.40, which is then a polar covalent bond. All right. So sulfur has 6 valence electrons, 2 openings. All right. So 2 pairs and 2 singles. And fluorine, of course, has 7 valence electrons, only 1 opening. Excuse me. So let's go ahead and put a fluorine around these 2 openings here. But here again, that's only SF2. In SF2, we have a normal octet for the sulfur and both fluorines. But here again, in period 3, we have the possibility where we can get extra fluorines around that sulfur because of an empty 3d orbital. Now, where are we going to fit 4 more fluorines? Because this is SF6. Well, around each of those unshared paired electrons right there. So this one's really going to get crowded. A lot of dots here, a lot of dots. Okay, well, let's draw that one. I'm going to have to erase the PCl5 here. Just don't have enough room. So here's what we got now. So S has 1, 2, 3, 4, 5, 6 fluorines around it. Let's get all the dots around the fluorines. So take a look at that molecule. It's really big, all right? So again, this is unstable because now, well, each fluorine has achieved its octet, 2, 4, 6, 8. But look around the sulfur. It's got 6 single bonds around it. 2, 4, 6, 8, 10, 12 electrons around the S. 12. So this again is an expanded octet. Phosphorus went to 10 electrons. Sulfur can go to 12. All right, again, because of that empty 3d orbital. It doesn't really like to be SF6. It's very crowded in there. And so again, normally this would prefer to break down to the normal octet between sulfur and fluorine, which we showed earlier briefly was SF2. And those other 4 atoms of fluorine will bond together in 2s and form 2 molecules of F2, or fluorine gas. So again, this is stable. We have normal octets here. So I just want you to be open to the possibility that for fluorine and sulfur, their octets can be expanded due to that empty 3d orbital in period 3 and that third energy level, whereby we can crowd some more atoms, some more bonds around phosphorus and sulfur when they are the central atom. Okay, so these are called, again, expanded octets. Now, one last one I want to show you, and it's just the opposite. This is basically a contracted or a smaller octet. Not really an octet at all. So let's take a look at that. And this involves the only nonmetal in group 3A, which is boron. Okay. So let's take a look at that. Boron will sometimes only have 6 valence electrons around it instead of 8. Remember, it's the only nonmetal in group 3A. All right. So let's take a look at that. So here's our compound BCl3. So boron's electronegativity is 2.04, chlorine 316. Subtract those 2 and we get 1.12, which is polar. Remember, between 1 and 166 is polar. So it's polar covalently bonded. So boron only has 3 valence electrons. 1, 2, 3. And each chlorine has 7. So boron has more openings. It's going to be in the center. So if we latch on a chlorine to each of those 3 electrons around boron, here's what you get. So we get BCl. Now I'm going to spread these apart. Remember, these bonds repel each other, so I'm not going to leave them straight across like that. I'm going to push them down a little bit. That's what's going to happen. So we've got this right here. So take a look at that. So we have each chlorine has 8 valence electrons. They're fine. They've achieved their octet. But now let's look at boron. It's only got 3 single bonds around it. 2, 4, 6. So this is unstable. Only 6 electrons around B. So this isn't an expanded octet. Technically, we call it a shrunken octet, but in reality, it's not really an octet at all, because an octet has 8, all right? And this boron only has 6 valence electrons around it. So that certainly is a shrunken octet, all right? It's only 6 instead of 8. And so again, this is unstable. So what does that mean? Well, what that means is this compound doesn't really want to stay like that. It's very reactive. Why is it reactive? Because boron needs 2 more electrons to complete its octet. And that's exactly what happens to it. So on the next page, this compound is relatively unstable and will react readily with compounds such as NH3 to form BCl3 and H3. Well, let's look at how that happens. All right, so here's BCl3. Well, I'll just leave it right here. We'll just do it up here. All right, so let's draw NH3, ammonia. All right, NH3, and remember it's got an unshared pair of electrons around that end. Okay, so here's an extra unshared pair, unused, and boron needs 2 more electrons. Nitrogen and boron are going to bond covalently. All right, the difference in electronegativities between those two is less than 1.67. Right here is a perfect scenario whereby one atom can share both electrons in a single covalent bond. Remember what that's called? I hope so. That's a coordinate covalent bond. Remember, it's a special type of single covalent bond where one atom donates both electrons in the shared pair. All right. And so what you end up with, and I'll draw that down here. So now we have B, Cl, Cl, Cl. And now here is our coordinate covalent bond to N, and then our H's. And that's BClNH3. Now look, the boron has 8 valence electrons around it because nitrogen has shared that extra unshared pair that it had with boron. So boron will exist where it only has 6 valence electrons, but it sure doesn't like it. All right, it's very reactive because it wants to pick up those 2 electrons so it achieves its octet. All right. And so what I wanted to show you here is that there are situations out there whereby compounds cannot possibly have every atom within that compound achieve its octet. Sometimes it's just not possible. And yet, those compounds exist. Well, they exist because of these possibilities right here. Phosphorus and sulfur can expand their octets to 10 or 12 electrons, respectively. Boron can actually form compounds where it doesn't make an octet and only has 6 valence electrons around it. We call that a shrunken octet. In every one of those cases, and others similar to them, we looked at NO2, which just has an odd number of valence electrons, total number of valence electrons, which means you can't possibly have every atom in a molecule like that achieve its octet. But yet, all of those compounds exist, which means they're there. So the situation isn't ideal. Those compounds all are unstable. They want to achieve their octets in some way, and so they become very unstable, very reactive, whereby they want to get to a situation where all atoms within those molecules achieve an octet, and that's normally exactly what they do. All right, and there are various ways for that to happen, as we have shown here. Okay, so just want you to be aware of not everything works out perfectly with the octet rule. All right, a majority of the time it does. All right, a great majority of the time, compounds, all the atoms within a compound do achieve their octet. That's the norm. All right, but sometimes it can't happen. All right, so, and I want you to see in what scenarios that can happen. So I think this will allow you to finish your assignment that we started on Friday. That is due tomorrow. I am collecting it for a grade. And other than that, that takes care of what we needed to do today. So until next time, this is Mr. Keister signing off. Take care, everyone. Stay safe. Keep working hard and stay focused. And I will catch you next time. So long, folks.